In this video, we'll look at solving this limit problem involving the limit of the difference between two cube roots. To solve this problem, we can use the fan favorite L'Hopital's rule for using algebraic manipulations. However, if we do it outright, it's gonna take a lot of writing and the solution is gonna be tedious and very prone to error. Trust me, I did it. I actually did it before recording this video and recorded it as another video, but the solution was too long and the video was much longer than I wanted it to be. So for this video, I took a step back and think about how to sort of simplify the solution and but if you want to watch that long solution that I did, mind you, that's the more straightforward solution, let me know and I can upload that anytime. But for this video, I'll show you how to do this in a short way, in a much shorter way. Note that as n approaches infinity, the value of n cubed plus 2n squared should always dominate 1. Actually, whatever the constant here, the n cubed plus 2n squared should dominate that constant. The same thing, in the same way, the n cubed here should dominate the negative 1 here. So in fact, this limit here is equivalent to the limit of the cube root of n cubed plus 2n squared minus the cube root of n cubed. We can simplify this by factoring out or taking out the n inside the, or taking it out of the radical. Note that if we factor out the n cubed, the first term should be n cubed times 1 plus 2 over n. So the second one simplifies just to be n. Write it again. It's gonna be n times the cube root of 1 plus 2 over n minus n. Simplify again by factoring out the n. We get n times the cube root of 1 plus 2 over n minus 1. Note that if we quote-unquote substitute infinity, we get here infinity times cube root of 1 plus, this one here should approach 0. So this thing here is 0. So we're basically having an expression whose limit is in the form infinity times 0. Note that the product is not 0, nor is it infinity. So don't make that mistake and do not equate that to infinity or 0. The correct way here is to rewrite the expression as this n here we'll rewrite as 1 over n, since that's equal to n. So the expression here is equivalent to the cube root of 1 plus 2 over n minus 1 all over 1 over n. Again, if we quote-unquote substitute infinity, it's gonna be 1 minus 1 over 0 or 0 over 0. So we can use L'Hopital's rule here. So this becomes the limit of the derivative of the numerator. We'll rewrite this as 1 plus 2 over n raised to the 1/3 so that we can easily use the power rule. Using the power rule and chain rule, we get 1/3 times 1 plus 2 over n to the negative 2/3 times the derivative of 1 is 0 times the derivative of, sorry, I'll just move this down. The derivative of 2 over n is negative 2 over n squared. And then the derivative of 1 is of course 0. The derivative of 1 over n is negative 1 over n squared. Now we just have to simplify this one. 1/3 times 1 plus 2 over n to negative 2/3 times negative 2 over n squared over negative 1 over n squared. The negative 1 over n squared and the 2 over n squared could cancel out to simplify to just 2. So the entire limit is just equivalent to the limit as n approaches infinity of 1/3 times 1 plus 2 over n to the negative 2/3. Evaluate at infinity, we get 1/3 times 1 plus 0, this approaches 0 as n approaches infinity, times, sorry, we missed the 2 here. So this becomes 2/3 times that, this is just 1, so the answer here is 2/3. Therefore, the limit of the expression that we're looking for is 2/3. And that's our final answer. Again, this is a shorter way of doing this. We've just rewritten the given limit by removing the constants, since the variable should dominate that constant as n approaches infinity. In that case, we have significantly shortened the solution. Hope you learned something from this video. Thank you for watching and please subscribe for more content.